Hello, this is a summary of hierarchical policy learning for mechanical search. Our goal is to create an agent which can retrieve target objects in a clutter. Therefore, we use a framework by Michael Danielczyk and others called mechanical search. The mechanical search pipeline consists of a perception pipeline and a search policy. The perception pipeline processes an RGBD observation of the scene, as well as a set of gallery images which serve as a description of the target object. It then outputs a binary mask for each of the detected objects, as well as a score which quantifies the similarity to the target object. Then, the object selection policy selects one of the objects for manipulation and forwards its mask to the action policies. Each of the action policies return a plan for the corresponding action and the probability of success for the planned action. The computed probabilities are then forwarded to the action selection policy, which decides which action to perform if possible. In this work, we propose hierarchical policy learning for the mechanical search problem. Further, we present two sub-policies which we optimize separately in a bottom-up order using reinforcement learning. Our push policy aims to increase the free space around our target object, which might help increasing the probability of success for future grasps. We optimize this policy using soft actor critic. Our action selection policy aims to minimize the number of actions for object retrieval through making optimal action choices. Here, we use a deep queue learning approach. We see a comparison between our approach and the original pipeline, which uses heuristics for pushing and action selection. After one unsuccessful trial, our policy decides for grasping the same object for a second time, while the original policy decides for a push action. The decision made by our policy led to retrieving the target object within 2 actions, while the original policy would require 7 more actions. In this graph, we compare the average number of required actions to retrieve a target object by the 4 policy combinations for 2 heap sizes. Each of the policy combinations and heap sizes has been evaluated for 100 simulated rollouts. It is noticeable that combinations which include our policies require less actions. This effect is more pronounced for the larger heaps. The second graph shows the number of successful object retrievals as function of the number of executed actions for the 4 policy combinations in heaps of 10 objects. Here, we see again that combinations which include our policies achieve higher success rates than the original heuristic policies. The last graph is for heaps of 20 objects. It is clearly shown that our policies outperform the original pipeline. While the success rate of the heuristic policy settles at 32% for 17 actions, our RL-based policies succeed in nearly 80% of the trials.